Long before the microchip existed, the modern computing world was built on something incredibly fragile: empty space enclosed in glass. This abstract physics model demonstrates a process called thermionic emission. When you heat a metal cathode inside a vacuum, it boils off free electrons, creating a one-way electrical flow across the empty void toward a positive anode. By inserting a third element, a metal mesh called a control grid, into this flow, we get a triode. A triode is a 3-electrode vacuum tube that can both switch and amplify electrical signals. By changing the grid's electrical charge, we can instantly choke or amplify the stream of moving electrons. Managing electron flow in a vacuum turned electricity into a medium for active calculation, moving beyond its basic role as a source of power. By the mid-20th century, manufacturing of these delicate glass tubes reached massive scales, driving global telecommunications and early radio networks. To build the very first supercomputers, engineers chained these tubes together by the thousands. During World War II, machines like Colossus relied entirely on massive banks of vacuum tubes to break German encryption codes. A few years later, the ENIAC machine utilized over 17,000 tubes to calculate complex artillery trajectories. Operating these early computers demanded immense physical space, often taking up entire rooms. But this early electronic infrastructure had a severe physical flaw. Thousands of glass bulbs operating at once meant a constant battle against burned-out components. Beyond their extreme physical fragility, these room-sized computing behemoths drew massive amounts of electricity and generated searing heat. The first computing infrastructure eventually collapsed under its own weight. The technology was strictly limited by the blistering temperatures and the massive physical footprint of its glowing glass engines. In 1947, physicists at Bell Labs invented the transistor, a tiny device made of semiconductor material that could replicate the switching and amplification of a tube without the heat or the glass. Instead of relying on a hot, fragile void, the transistor utilized a cold, solid block of crystalline silicon to control electrical current. Because they required no vacuum and no heating element, transistors enabled extreme miniaturization. Computers shrank from the size of living rooms down to units that could easily fit in a pocket. As production of these tiny silicon switches scaled globally, the technology industry universally declared the vacuum tube obsolete. Yet the vacuum tube survived in hidden, extreme-stakes environments where solid-state silicon physically fails. This split-screen diagram shows exactly why. On the left, electrons move at high speeds through the clean, empty vacuum of a tube, easily handling massive voltage spikes. On the right, the flow is restricted and friction-heavy as electrons struggle to push through a solid silicon crystalline lattice. That empty space gives the tube a supreme advantage in military applications. Vacuum tubes are completely immune to electromagnetic pulses, massive bursts of radiation from nuclear blasts that instantly fry solid-state silicon. This is why the Soviet military relied on vacuum tubes for the radar systems in their MiG-25 fighter jets, long after transistors had become the global standard. You can also find them today in high-end audiophile amplifiers and household microwave ovens, where raw analog power is strictly prioritized over microscopic size. Silicon excels at miniaturization, but for extreme power and indestructible resilience, an empty void remains the ultimate physical environment. Today, modern computing faces a crisis. Moore's law, the historical observation that the number of transistors on a microchip doubles roughly every 2 years, is hitting a brutal physical wall. We are now packing billions of transistors onto single chips. At that microscopic density, the silicon components leak electrical current and generate catastrophic amounts of heat. Modern solid-state silicon is dying from the exact same heat and density limitations that killed the vacuum tube 70 years ago. To solve this critical physical bottleneck, researchers around the world are turning to a groundbreaking hybrid technology called vacuum nanoelectronics. Scientists are taking nanoscale transistors and carving out the solid material, leaving a distinct gap of empty space. Because this gap is so microscopic, electrons jump between the points using a cold cathode, releasing charge without any glowing, heat-generating filament. Aerospace institutions, like the NASA Ames Research Center, are actively developing these vacuum channel transistors to survive deep space missions and heavy radiation environments. By bridging the microscopic manufacturing scale of silicon with the frictionless physics of the 1904 vacuum tube, researchers are using a century-old discovery to bypass the current physical limits of the microchip.